In every car accident, there are actually three distinct crashes. The first is the car hitting the wall. The second is your body hitting the seatbelt. But the third crash is the silent killer. It's when your internal organs slam into the inside of your own skeleton. Stopping that third collision is the hardest problem in mechanical engineering. How do we keep a human body safe when the car stops instantly? In this video, we'll explore the mathematical equation that rules your survival, the dark history of human testing before dummies existed, and why modern cars are engineered to sacrifice themselves to buy you a fraction of a second. What is G-force? Let's start with the villain of the story, G-force. Right now, sitting in your chair, you are feeling 1 G. That is just gravity pulling you down toward the center of the Earth. If you weigh 70 kilograms, 1 G feels like, well, 70 kilograms. But acceleration is a multiplier. If you pull 2 Gs, you effectively weigh double. At 10 Gs, you weigh as much as a small car. Your bones are strong, like concrete. They can handle compression. But your blood? It's a liquid. It's heavy. At high sustained Gs, your heart isn't strong enough to pump blood up to your brain. That's why fighter pilots pass out. But in a car crash, the Gs aren't sustained. They are sudden. Here is the equation that rules your survival. Acceleration equals the change in velocity divided by time. Look at the t at the bottom. This is time. Because it's in the denominator, if time gets smaller, acceleration gets huge. Think of it like catching an egg. If you throw an egg into a bed sheet, the sheet gives way. It slows the egg down over maybe half a second. The time is large, so the force is small. The egg survives. If you throw that same egg at a brick wall, the stopping time is almost 0. When you divide by 0, the force approaches infinity. The egg explodes. If you go from 60 to 0 in 1 second, that's about 2.7 Gs. Uncomfortable, but survivable. If you go from 60 to 0 in 1/100th of a second, that is nearly 300 Gs. That is a fatal load. The goal of every safety engineer, therefore, is not to stop the crash. It is simply to buy you time, even milliseconds. So how do we know what the human limit is? How do we know that 40 Gs breaks a rib, but 50 Gs ruptures an aorta? Well, the history of crash testing has a dark chapter. Before we had plastic dummies, we had volunteers. And by volunteers, I mean cadavers. In the early days of automotive research, universities actually used donated bodies to see how much force it took to fracture a skull against a steering wheel. While it sounds gruesome, it provided the baseline data for every seatbelt we use today. But it had a massive scientific problem. You can only test a cadaver once. Every test subject was different. Different ages, different bone densities. You couldn't create a standardized scientific control group. We needed a live subject. Enter Colonel Stapp, the fastest man on Earth. In the 1950s, Stapp didn't trust dummies. He believed the only way to test human tolerance was to test a human. He strapped himself into a rocket sled, blasted across the desert at 632 miles per hour, and came to a dead stop in 1.4 seconds. He experienced 46 Gs. His ribs cracked. His retinas detached. He was temporarily blinded. But he proved that the human body could survive forces far higher than anyone thought, if they were properly restrained. But obviously, we couldn't ask Colonel Stapp to crash a car every Tuesday. We needed a repeatable human, something we could kill 1,000 times without filing any paperwork. We needed a robot skeleton full of science. Anatomy of a dummy. Enter the crash test dummy, specifically the Hybrid 3, the industry standard since the 70s. A modern dummy is not just a mannequin you find in a clothing store. It is a precision instrument that costs upwards of $500,000, often more than the luxury cars it is destroying. Let's look inside. Inside the aluminum skull, 3 accelerometers measure G-force in the X, Y, and Z axes. They tell us exactly how fast the brain is moving inside the skull. The neck is calibrated with rubber discs to mimic the exact flex of a human spine, measuring whiplash torque. Inside the chest, steel ribs are lined with a special damping material to mimic human flesh. Behind those ribs is a potentiometer, basically a digital ruler, that measures exactly how many millimeters the chest is crushed. If the ribs compress more than 65 millimeters, the test fails. That represents a collapsed lung or broken ribs in a real person. Now, you might ask, why don't we just simulate this on a computer? We have AI now. We do use simulations, millions of them, but simulations are only math. They are approximations. In the real world, steel tears unpredictably, welds snap, plastics shatter. If the math says you survive, but the physical dummy loses its head, you trust the dummy. The paradox: weaker is stronger. This brings us to the most counterintuitive fact in engineering. To save the passenger, you must destroy the car. People often look at old cars from the 1950s, those giant steel tanks, and say, they don't make them like they used to. And thank goodness for that. If you build a car like a tank, rigid and tough, it stops instantly when it hits a wall. Remember our equation? Small time equals big force. The kinetic energy of the car has to go somewhere. Since the metal didn't bend to absorb it, that energy travels through the chassis, into the seat, and directly into you. The car survives, but the passenger doesn't. But look at the modern car. The front is designed to crumble like an accordion. It looks catastrophic, but that crushing action takes time. It might only extend the crash from 20 milliseconds to 100 milliseconds. But in the world of G-force, that is an eternity. The bending metal is doing work. It is converting your kinetic energy into heat and sound. Every piece of metal that bends is energy that isn't breaking your bones. The car dies so you can live. Not all humans are average. Since the 1970s, the gold standard has been the hybrid 3, 50 percentile male, roughly 5'9", 172 pounds. For decades, safety ratings were built around this one body type. But physics doesn't treat every body equally. A seatbelt that fits him perfectly can ride up on a smaller frame, causing internal injuries. Optimizing for the average, quietly engineered risk for everyone else. We needed higher data resolution. Enter THOR. While a standard hybrid 3 might rely on about 30 data channels, the THOR device packs over 140 sensors. It tracks rib deflection and spinal motion with far greater precision. True safety isn't about protecting a statistical myth. It's about gathering enough data to protect the variance of reality. So next time you see a slow-motion video of a car smashing into a block, remember, you aren't watching destruction. You are watching a machine sacrifice itself, guided by a plastic hero that has died 1,000,000 times, so you don't do so if you get unlucky on the road. Thank you so much for watching. If you enjoyed this video, please consider subscribing, liking, and sharing this video with other people interested in simple engineering.